Hello everyone, welcome to this video. Today, let's talk about the heart of electric vehicles, the power battery. We all know about Tesla's V4 supercharger, which has a maximum output power of 600 kW. Meanwhile, BYD recently introduced its highly popular 10C ultra-fast charging system with a maximum power of 1000 kilowatts. With such high-power charging, do we have some questions? For example, can the national power grid supply such a high power? How do these fast charging stations alleviate grid pressure? How do batteries handle increased heat under ultra-fast charging conditions? The answer is that these fast charging stations are equipped with large-scale energy storage systems. They charge at low power and store energy under normal conditions. When fast charging is needed, this energy reservoir rapidly discharges, providing high-power charging while reducing stress on the grid. Additionally, a powerful battery management system, BMS, ensures battery stability. However, a more interesting question is, how do batteries operate under such high charging power? This leads us to today's core topic, the mysteries of battery charging and discharging and battery types. Next, we will take a deep dive into the principles of battery charging and discharging, as well as the differences and types of mainstream power batteries on the market. During charging, lithium ions detach from the cathode, pass through the electrolyte and separator, and finally embed into the anode. During discharge, lithium ions return from the anode to the cathode, generating current to drive the vehicle. However, this process is far more complex than it seems. Lithium ions must overcome three major obstacles. The first is the desolvation process. The electrolyte, lithium ions, are usually bound to solvent molecules, like wearing a protective coat. Lithium ions must detach from these solvent molecules and become bare ions. This desolvation process requires overcoming a significant energy barrier and is the most energy-intensive step in the charging process. The second is passing through the SEI film. A solid electrolyte interface (SEI) film forms on the anode surface, preventing side reactions between the anode and the electrolyte. However, it also creates a barrier for lithium ions. As charge cycles increase, the SEI film thickens, making it harder for lithium ions to pass through. The third is embedding into the anode material. The anode material is usually graphite, and lithium ions must intercalate between the graphite layers, although the interlayer spacing is approximately 335 nanometers. Lithium ions must overcome the repulsion of the electron cloud, prompting local electron cloud rearrangement and structural reorganization. This reduces the energy barrier and allows lithium ions to embed into the anode. This step is critical for determining charging speed and efficiency. These three obstacles determine the battery's charge-to-charge rate, efficiency, and cycle life. Every detail is crucial, making lithium battery research a highly sophisticated science. Now that we understand the charging and discharging principles, let's look at the differences in mainstream power battery types, capacities, and characteristics. Ternary lithium battery (NMC). This type of battery has a cathode composed of nickel, cobalt, and manganese, each serving a different function. Nickel increases battery capacity, cobalt maintains structural stability, and manganese enhances heat resistance. Its greatest advantage is high energy density, meaning it can store more energy per unit weight. Currently, it is around 200 Wh/kg and could increase to over 260 Wh/kg in the future. However, the higher the nickel content, the more the battery tends to heat up, affecting safety. Therefore, engineers must find a balance between range and safety. Lithium iron phosphate battery's cathode material is lithium iron phosphate and the anode is graphite. Compared to NMC batteries, LFP batteries have advantages such as safety, longer lifespan, and lower cost. They are less prone to catching fire and are more durable. However, their energy density is lower, typically around 150–160 Wh/kg. Due to its relatively limited range, It is more suitable for household electric vehicles and buses that do not require ultra-long driving ranges. Solid-state battery uses a solid electrolyte, which is safer and structurally more stable than traditional liquid electrolytes. Theoretically, solid-state batteries can provide higher energy density, longer lifespan, and faster charging speeds. However, they currently face many technical challenges, such as low ion transport efficiency and material compatibility issues, so they have not yet been commercialized on a large scale. But the future looks promising. The three major obstacles in the battery charging and discharging process: desolvation, crossing the SEI film, and embedding into the anode material determine the battery's performance and lifespan. We also compared three mainstream power batteries, highlighting their differences in materials, charging and discharging principles, energy density, and application scenarios. In the future, with advancements in new materials and technology, we may see further improvements in battery energy density, continuous reductions in charging time, and even the realization of the dream of a single charge for 1,000 kilometers. Have you ever felt anxious due to long charging times? Feel free to share your thoughts in the comments section. Thank you for watching. If you have more questions about battery charging and discharging principles or different types of power batteries, remember to like, subscribe, and leave a comment. See you in the next video. Bye.